Hi everybody, let's talk about how to do these various calculations involving aqueous solutions. So to begin, let's start with a fairly simple one of just reading off of this to answer how many grams of ammonia gas are soluble in that much water. So what you do when you solve these is, of course, start with your given 712.5 grams of H2O, and then you set up the conversion factor to get from what you're given to what you're being asked, how many grams of NH3. So grams of NH3. What you're going to do is read off this chart to figure out how many grams of ammonia are soluble per 100 grams of water. So what we do is we look at the temperature, 25 degrees Celsius, find it on here, it's roughly here, and we trace this up and find the ammonia line, which is right there, and it looks like it crosses right at 50. So from 25 right here, and then follow it over, 50 grams soluble. So we put 50. But this isn't 49 or 51, this is 50 exactly. So 50 with a decimal grams of NH3, aka ammonia. And that's per 100 grams of water. And this is infinite sig figs, this is 2, and that is 4. So we're going to do a calculation that's going to give just two significant figures. So let's see what that would be. It would be that number of grams. So I'll write the unrounded raw calculator answer of 356.25 grams of ammonia should be soluble, and then rounding for significant figures, 2 sig figs, so that is 360 with no decimal, that way it stays as 2 significant figures, grams of, ammonia. There we go, 360 grams of ammonia. All right, so that's two significant figures as it should be, based on that estimate. Now for here, this is a different kind of question. Instead of how much will dissolve, how much out of this amount will dissolve in that much water at that temperature. So once again, in order to, once again we're doing a calculation of how much can dissolve, because we're going to figure out how much can dissolve and then subtract it out of the amount that was put in there. So that means beginning actually in a very similar way with the grams of water, since the grams of water determines how much will dissolve. 413.8 grams of water. And then we'll multiply by a conversion factor with grams of water on the bottom, so that gram cancel grams. And then we're going to figure out how many grams of potassium chlorate will dissolve at that temperature. Now, according to the y-axis, that's per 100 grams. So we just look it up on here, and it is at 50 degrees Celsius, so we find 50. And I follow this up to find the potassium chlorate line, which is this one right here. So 50, there's potassium chlorate, it's this line. And I follow it over, and it looks like about 21. I'll estimate 21 grams of potassium chlorate per 100 grams of water. So that would be what number? Well, let's calculate that out. That number, 86.898 grams of KClO3 dissolves. So that's what we have so far, is the idea of, okay, if that much dissolves, sig figs, 2 sig figs, 87 grams of potassium chlorate will dissolve. But don't box that, it's not the final answer. It wants to know how much will be left over. So clearly not all of it will dissolve, only 87 grams can dissolve, 105 grams are added, so there will be something left over. So we're not going to write all will dissolve, because something's going to be left over if you add more than can be held by the solution. So what we're going to do is we're going to take 105.0 grams KCl starting, and we're going to subtract 87 grams, KClO3, KClO3 dissolved. That will tell us how many grams of KClO3 left over. So if you do the math on that, then what you get is 18 grams of potassium chlorate. Now underline here, draw an arrow pointing at it. Okay, 18 grams. technically I guess it would have been 18.0, but because the arrow points here, it just turns into 18 grams of potassium chlorate remains. So not all will dissolve. Instead you have that. If this calculation had yielded a number greater than 105, then you simply would have written the words all will dissolve in a box, and that would have been the final answer. So that's how you handle that one. Now moving on, let's see if I can, there we go, okay. So how many grams of this solution contains that many grams of sodium chloride in 21.07% by mass solution? The answer is you are going to need the formula. Percent mass equals mass of solute over total mass of solution, which is solute plus solvent. So I'll just put mass of solution, that's the standard abbreviation for solution, times 100%. I may have phrased it different in the notes, but it's the same idea. So what you're going to do is note that how many grams of solution contain, so it's asking you solve for this. So I need to do some algebra to get this by itself. So I'm going to multiply both sides by mass of solution. If I multiply both sides by mass of solution, then mass of solution times percent mass equals mass of solute times 100%. Again, we need to solve for this, which means divide both sides by percent mass. So that cancels. Divide both sides by percent mass. And then what we have is mass of solution equals mass of solute times 100% divided by percent mass. And since that's the answer we're trying to get, let's plug in the numbers. Mass of solute is that 95.332 grams of sodium chloride times 100% divided by, and what percent mass? At 21.07% mass. And then we just do the math on that, and when you do the math, you get that answer. So raw calculator answer of 452.4537257 grams of sodium chloride solution contain that many grams of sodium chloride. And we're going to round that for sig figs because you have 5 sig figs, infinite sig figs, and 4 sig figs. So 4 sig figs is the answer. 452.5 grams of sodium chloride solution contain that many grams of sodium chloride if the solution is that percent of mass. And that's how you handle that one. So let's look at another one. So calculate the molarity of a solution produced by dissolving that many grams in enough water to make that many milliliters. So my favorite shortcut is to notice that molarity, which is moles per liter, essentially take whatever number that's going to turn to moles. This will turn to moles, so you're going to put it on top. And whatever turns into liters, you're going to put it on bottom. So this number will go up here. This number will go down here. So what I'm going to do is I'm going to take 7.94 grams of sodium nitrate divided by 69.8 milliliters of solution. You want to have a chemical identity by the mass because that will make a big difference depending on what it is. Like different chemical identities make the mass mean very different things when it comes to converting to moles. For the volume, it doesn't really make a difference. Volume is volume no matter what chemical identity. So that's why I left off the chemical identity here. But that said, let's move on. I need to convert this to moles. I need to convert this to liters. Doesn't matter which one I do first, so I'll just do the mole one first. So I'm going to put grams of sodium nitrate on the bottom, and I'm going to put moles of sodium nitrate on top, which means we need to figure out what's the molar mass of sodium nitrate, but 1 mole will have that many grams. So that just means I need to find sodium nitrate, which is 22.99 grams per mole for sodium, and then 14.01 grams per mole, that's nitrogen, and then 3 times 16.00 grams per mole, that's oxygen. If you add that all together, that's the molar mass, which your calculator will tell you is this, but don't be fooled. That's 85.00 grams per mole, because hundreds place, hundreds place, hundreds place, hundreds place. Sodium nitrate. So I'm going to put 85.00 grams there. But that's going to be gram cancels gram to give moles on top. That's good. Now this needs to be liters. So I'm going to put I'm going to put liters down here and milliliters. Now it turns out that a milliliter is 10 to the negative third liters. Alternatively phrased, you could also say that 1 liter is 1,000 milliliters. It doesn't really matter which one you do because they both give the same answer. So I suppose what I'll do is, for no particular good reason, I'll just leave it like this, even though it's going to be mathematically the same to put 1 here and 1,000 here because there's 1,000 milliliters in a liter. Anyway, if you just check the units, milliliter cancels milliliter, gram cancels gram, and now you have moles per liter, which is molarity. So if you do the math on that, let's see what it comes out to. Okay, 7.94 divided by 69.8 equals, divided by 85 equals, divided by 10 to the negative third, close parentheses, equals, and that's what you get. 1.338277431. Oops, that's what I get for looking at this rather than this as I write. What are the units? Moles per liter. Now let's round that. 3 sig figs, 3 sig figs, 4 sig figs, infinite sig figs for metric conversion. So you're using a 3 sig fig answer. So we're going to round that to 1.34 moles per liter, or just write capital M, either one's fine, sodium nitrate, and then you box that. Well, now do this one. Give the concentration of all ions in that solution. Okay, here's how that's going to happen. How many ions are there? There's 1, there's 2. Calcium and phosphate. So what I'm going to do is start with 0.0673 molar calcium phosphate. And then what I'm going to do, and you could write moles per liter for this one too, it's fine. But I'm going to take advantage of the fact that you can look at this and be like, oh, well, okay, all the ions. Let's do a calculation for calcium. Let's see, what unit do I want to use? I'll use a mole-mole ratio. PO42. Or you can just write numbers. It doesn't matter particularly in this particular instance. Just for every 1 mole of this, notice how there's 3 moles of calcium. I'll put 2 plus ion. Essentially, we're just taking this number and multiplying it by 3. And that gives that. So 0.2019 molar calcium 2 plus ion. And then we're going to round that for sig figs to 3 sig figs, 3 sig figs. So you're going to have to call that 0.202 molar calcium 2 plus ion. Now we're going to take the same approach to the other ion, 0.0673 molar calcium phosphate. And the only difference is we're going to do for phosphate this time. So 1 mole of calcium phosphate, rather than looking at calcium this time, now we're looking at phosphate, contains 2 moles of phosphate. Okay, we're all good why that's 2 moles of phosphate, hopefully. So 2 moles of phosphate for every 1 mole of the entire compound. So the math on that is going to give an answer of that 0.1346 molar phosphate. We're going to round that for sig figs because it's 3 sig figs, infinite sig figs, so 3 it must be. 0.135 molar phosphate. You put a box around that, and that's how you handle that. All right, onward. Okay, so now we're looking at how many grams of potassium bromate is needed to make that many milliliters of that molar solution. Okay, so in order to do that, what we're going to do is we're going to take a couple little looks at this, but I think the best way is to use these two to separate out the unit of molarity into moles and liters, and then get moles. And then once you get moles, we're going to take the moles and turn it into grams. So let's start with understanding, hopefully all is clear, that this is moles per liter. If I can turn this into liters and then cancel them, it would become just moles. And then you can use the molar mass to turn that into grams. Which means before I even get going anywhere, because I know I'm going to go from moles to grams, might as well set up with the molar mass. So potassium bromate. So as you can see here, I've got the molar mass figured out, and we're going to use that to get the grams. Now, in order to make this work, we can start with either of these to begin our calculation. I suppose maybe for no particular reason I'll start with this one, but I could have started with this one too. So 6.500 moles of KBRO3 per 1 liter. Okay, hopefully it's all clear how molarity turns into that many moles per liter. And then we're going to take care of the given. We're going to want liter to cancel liter so we can get moles and turn into grams. So I'm going to put it times 250.0 milliliters. Now the thing is, like, milliliters does not cancel liters, so I need to add another unit in there. I need to put milliliters on bottom, so milliliter cancel milliliter. I need to put liters on top, so that liter cancel liter. And it turns out that, yeah, 1 liter is equal to 1,000 milliliters, or you can likewise say that 10 to the negative third liters is equal to a milliliter. We don't really care which one you use. On this particular one, I'll just say that 1 liter is equal to 1,000 milliliters. Not that it matters, both ways are equal, it's mathematically identical. But in this particular scenario, what this does now, check it out. Liter cancel liter, milliliter cancel milliliter, you're going to get moles. And then what we can even do is add another conversion factor and put moles on here, KBRO3, so that moles cancel moles, and put grams of KBRO3 so that you can have it as your answer. And grams and mole, what's that from? That's your molar mass. 167.00 grams per mole is the mass of potassium bromate. So essentially it's just this times this divided by this times this. And again, it doesn't even matter. I mean, you know what? Just for no particular reason at all, I'll switch it around again. 10 to the negative third liters is a milliliter. So let's do that math. 6.500 times 250 times 10 to the negative third. Second function, 10 to the x negative third. And then times 167. So, well, there you go. By the way, if instead of multiplying by this, if I divide by 1,000, the answer would have been exactly the same. All right, well, 271.375 grams of potassium bromate which we'll round for sig figs, infinite, 5, 4, and 4. So 4 sig figs it is, determined by those, 271.4 grams of potassium bromate is needed to make that many milliliters of that molarity of solution. Okay, let's look at another. Okay, stoichiometry this time. Calculate the mass of solid lead 2 chloride that would be formed if excess potassium chloride was added to that many liters of that solution. So it's asking information about one chemical, but giving you information about a different one. That is stoichiometry. You do need a balanced equation, because now instead of giving you information about one chemical and asking about the exact same chemical, now it's asking about a different one. So it says what mass would be formed. So that tells me that it's a product. This is added to this. Those are your two reactants. So lead 2, it doesn't matter what order they are, so I'll put KCl and then work backwards to see the lead 2 nitrate. PbNO3 All right. And then of course you can't forget that like the potassium doesn't just disappear, the nitrate doesn't disappear. Potassium is a 1 plus, nitrate's a 1 minus. That is the correct formula for the combination of potassium and nitrate. So you the viewer, you have to come up with that on your own. The rest of this is stated right there in the question. And you need this because you need a balanced equation. There's 2 nitrates, so you better have a 2 here, but that's 2 potassiums. Oh, you better have a 2 here, and that's 2 chlorines. Oh, good, you've got 2 chlorines. All right, now it's balanced. Now you can go out and actually do this reaction. So once again, first thing you're going to write is your givens. Does it matter which order? No. Last time I started with this one, turning into moles per liter. Back up here in that calculation. But it doesn't really matter. You can start either way. So you know what? I'll start with the liters because whatever. This has like a fraction with a unit on top and bottom, and this is just one single unit. So I think it looks a little prettier when you start with a simple unit like just liter anyway. So 1.25 liters times. And then let's see, what are we doing? Well, let's see. Liter will cancel liter to give moles. Well, that's good. That's a good start toward getting mass. So 1.750 moles of, what is this, lead 2 nitrate per 1 liter. So liter cancels liter. We've already got moles of lead 2 nitrate, but it's not asking for moles of lead 2 nitrate. It's asking for a mass of solid lead 2 chloride, so different chemical. And like always, if you have 2 different chemicals, you need to go from one to the other using the mole-mole ratio. In this case, for every 1 mole of lead 2 nitrate, there is 1 mole of lead 2 chloride. Dear viewer, just note for grading of the test, because the 1-to-1 ratio, yes, it's true you could skip this and still get the right answer, but if a person has the right answer but skipped this, there will be a significant point deduction or potentially a 0 depending on exactly how things were done. So even if it doesn't make a difference, always include the mole-mole ratio. Or at least even if it doesn't appear to make a difference to the uneducated viewer, the educated viewer should know that it makes a difference and should definitely include this, even when it doesn't change the numerical outcome. So moles of this chemical cancels moles of this chemical, give moles of lead 2 chloride. And then what we're going to do is say, put moles of lead 2 chloride here, so that moles cancel moles. I'm going to use the molar mass to have grams per mole of lead 2 chloride. Oops. And that will allow me to get a final answer in grams. So the mass of 1 mole of lead 2 chloride turns out to be 278.1 grams. Why not the hundredths place? Because lead has a molar mass ending at the tenths place, which means if you use this in your calculation, whatever mass involving lead will always go no further than the tenths place. Tenths place. All right, well, given that number, it is now time to do the rest of the calculation. So this times this times this. And the answer is that number. That is the mass that would be formed. 608.34375 grams of lead 2 chloride. Round for sig figs. 4. Infinite. 4. 3. 608 grams of lead 2 chloride. Oh, let's box that, of course. All right, well, on to the final question, I suppose. Oops, I just knocked it sideways. There we go. Okay. Let's get this a little more oriented. There we almost go. All right. Anyway, so it gives you these two reactors, reactants. That's a product. How many milliliters of this are needed to completely react with that many milliliters of that? All right. In order to do anything, we need to start with a balanced equation. A balanced equation is required for credit. So we do know that lithium sulfate reacts with silver iodide to produce silver sulfate. And then it doesn't state it, but you should be able to figure out that lithium, if not paired with sulfate, must pair with iodide. It turns out that's the correct formula for lithium iodide. Balancing the equation, 2 silvers, 2 silvers, which means 2 iodines, 2 iodines, 2 lithiums, 2 lithiums. Oh, good. That's set. All right, now that's all dealt with. How many milliliters of this are needed to completely react with that? So my strategy is to start with this, because the volume and the molarity is needed to really to do anything. And then this will tell me how many moles of the silver iodide, because this is moles per liter. So convert this to liters. This liters will cancel with this liters to give moles. We can then turn moles of this into moles of this. And then if we take the molarity, we can turn moles into a volume. Let's actually do that now. So I'm going to take the 75.0 milliliters, and what I'm going to do with that one is I'm going to multiply that by use this 0.500 moles of silver iodide, and that will be over 1 liter for this one. This is also the silver iodide. And then what I'm going to do first is make sure that this gets turned into liters. So what I'm going to do is put milliliters, oops, wrong place, milliliters on top and liters on bottom. Okay, my bad, I'm all confused. Let's fix that. Milliliters on bottom, liters on top. Apologies, that's how it's supposed to be in the first place. That way liter cancels liter, and milliliter will cancel milliliter. There we go, that's how it's supposed to be. As before, you can put 1 milliliter is 1,000 milliliters, or sorry, 1 liter is 1,000 milliliters, which is fine. You can also put that 10 to the negative third liters is a milliliter, also fine. Either's good. Next thing that's going to happen is moving on to the next, well, okay, so we check. Milliliter cancels milliliter, liter cancels liter. Cool, now you got moles of silver iodide. Because you're given information about one chemical and asked to find about a different one, this is when you need the stoichiometry. So I'm going to put moles of silver iodide here, so that moles can cancel moles. And then I'm going to put moles of what I'm trying to find on top. So I am trying to find moles of what? Moles of lithium sulfate. Lithium sulfate. Now if we look at the balanced equation, 1 mole lithium sulfate reacts with 2 moles of lithium iodide. So now silver iodide. So now moles of silver iodide cancels moles of silver iodide. I now have moles of lithium sulfate. I'm trying to find volume of lithium sulfate. So here's what I'm going to do. I'm going to take that molarity, remembering that it's moles per liter, and I'm going to put moles of lithium sulfate on the bottom so that moles can cancel moles. And I'm going to put the liters up top. Technically liters of lithium sulfate, I guess. But see this molarity? That's 0.125 moles per liter. This is this. See how moles is on bottom now so that it can cancel this and give liters. At this point, all the units except for liter cancel. So I'm going to get liters of lithium sulfate. But it didn't ask for liters, it asked for milliliters. So I'm going to have one more conversion factor. Liter on bottom, so liter cancels liter, and milliliter on top so that it gives the answer we're trying to get. And you either write 1,000 milliliters as a liter, which is fine. You can also write that 1 milliliter is 10 to the negative third liters. Doesn't matter. I just realized that looks like a plus. So let's just make it clear that's minus 3. Doesn't matter, okay? It could be 1,000 milliliters to a liter. Whatever you do, you're going to get the same result. Because if you do the math, it's this, times this, divided by this, divided by this, divided by this. Okay, so you do the math and, let's see, there you go, found it. Let's see, 75 times 0.500. All right, this, sure, times 10 to the third. Oops, negative third. Divided by 2. Divided by 0.125. Divided by 10 to the negative third. And you get that number there. 150, exactly. Now, wait, how are you going to round this? 3 sig figs, infinite, infinite, 3, and infinite. 3 sig figs, put a decimal. 150 exactly milliliters of 0.125 molar lithium sulfate are needed. So in other words, we just calculated that this many milliliters of this solution are needed to completely react with this many milliliters of this solution. We'll box that answer. And there you go. That gives an answer. That's it.